Okay, students, good morning, all of you. Today also we are going to discuss about geometrical isomerism. This is our third lecture on geometrical isomerism. This is very important class. Really, if you are preparing for mains and advanced seriously, this class is very important. Why? Because now here also we are not going to apply any general formula just by the arrangement of atoms and groups according to the given molecule. So we are going to write total number of geometrical isomers. Okay, right. So now let us start from the first question. Now this is my first question. How many how many of the how many of the structural isomers of C2 fluorine, chlorine, bromine and iodine will show geometrical isomerism? Very good question, very important question, right? Once again, read that question. How many of the following structural isomers of C2F chlorine, bromine, iodine will show geometrical isomerism? They are giving one molecular formula, right? Two carbon atoms are there, and how many halogen atoms are what present? Four different halogens are there: fluorine, chlorine, bromine, and iodine, right? Here, what is the question given? According to that given molecular formula, now it has some structural isomers, right? For example, if you are going to write by the arrangement of atoms, now you are getting some structural isomers. Here the question is, from the possible structural isomers, how many structural isomers are responding for geometrical isomerism, or how many of the structural isomers will show geometrical isomerism? That is our question. Okay, here answers also I am giving like this. Now first option, second option, third option and fourth option. Now answers they are giving like this: 3, 6, 9 and 12. What is the right option? Very important question and very good question, right? Very simple also, no problem. Yeah. So in order to solve this question, actually here the main problem is, according to this given question, sometimes we are getting confusion and straight away we are going for second option, but actual right option is, what is the right option for this question? Now we will check, right? One second. Yeah, let us solve this problem. So first of all, we want how many number of structural isomers which are responsible for geometrical isomerism, right? Basically, whenever the given compound is given, first you think about what is the minimum condition for geometrical isomerism. Minimum condition we want, what is the first condition? Restricted rotation of CC bond. According to the given molecule, here only we have carbon atoms. That's why I am thinking about restricted CC bond rotation. So where we observe restricted CC bond rotation? Now in case of unsaturated systems like alkenes, okay. Now in cyclic compounds also restricted rotation is possible, right? But here with two carbon atoms, we are not writing any cyclic compound. Cyclic compound is not possible with two carbon atoms. Here only two carbon atoms are there. With two carbon atoms, there is no chance to write the cyclic compound. That's why simply I am going to take C double bond C. C double bond C. Yes. After writing that C double bond C, now that C double bond C is providing free rotation of CC bond or restricted rotation of CC bond? Yes, restricted rotation of CC bond. Yes, we got first condition for geometrical isomerism. Now we have restricted CC bond rotation. Your two carbon atoms are completed, and these two carbon atoms are connected through the double bond, right? They are what part of double bonded system. And according to the given molecular formula, we have now four halogen atoms are there, four different halogen atoms. Now just I am trying to arrange these four halogen atoms on the carbon atoms, right? Okay, let us start from this one. Just I am taking now fluorine. Conveniently, what we are doing here, we have four different halogen atoms. One halogen atom just I am trying to keep at fixed position, at least one halogen. Sir, which halogen we select? According to your wish, you can select either fluorine, bromine, chlorine or iodine. Among the four halogen atoms, any one halogen atom you can select. But the thing is, that halogen atom just you fix at fixed position. Okay, here I am taking fluorine. And what are the remaining halogens? Three halogens are there. Now in first structure, I am taking fluorine here. Here also same thing, just I am trying to fix the position of fluorine. Here also same thing, position of fluorine. Clear? We are not going to change position of fluorine. and we have chlorine, bromine and iodine. Chlorine, bromine and iodine. These halogen atoms, just I am trying to arrange on the carbon atoms. Here I am taking that chlorine. Chlorine, okay. Next remaining bromine and iodine. This is my first structure. But in the second structure, I am taking another structural isomer. In second structure, I am taking here bromine. Okay. Here chlorine, but here bromine. And what are the remaining two halogen atoms? Chlorine and iodine atoms are left. For example, if you start from here iodine, fluorine and iodine, then what are the remaining? Chlorine and bromine. These are the maximum possibilities. Okay. Once again come back to our same question. How many of the structural isomers of C2F, chlorine, bromine and iodine will show geometrical isomerism? So according to the given question, first I am going to write the structural isomers of the given compound. These are my structural isomers. So what I am doing here, first I am trying to fix one halogen atom without changing its position, and remaining halogen atoms just I am trying to change like chlorine, bromine and iodine. So if you are taking chlorine here, remaining two halogen atoms comes onto this carbon atom, and if you are writing bromine here, remaining chlorine and iodine coming onto this carbon atom, like that. Okay, these are the possible structural isomers. Now these structural isomers, after writing these structural isomers, now just you look at on this sp2 carbon atom, right? This is our sp2 carbon atom. Now verify the groups fluorine and chlorine. These two group atoms same or different? They are different. Bromine and iodine same or different? They are different. So definitely this structural isomer will show geometrical isomerism. Okay, next one, fluorine and bromine, these two same or different? These two are different, right? And come to the next carbon atom. Here chlorine and iodine atoms are present. These are also different, right? This molecule also shows geometrical isomerism. Like that, here fluorine and iodine connected and chlorine bromine connected. Yes, this molecule also shows geometrical isomerism. But here what is the right option? First of all, we are writing three structural isomers. From that, every molecule will show geometrical isomerism. What is our right option? This is our right option. Okay, 3 is the exact answer for this question. But where we are getting confusion, the main problem is actually after writing this structure, after writing that structure, sometimes what we are doing mistake, again we are taking C double bond C. Now here fluorine and chlorine, either side, from left side or from right side, we are exchanging the groups. Like now here iodine I am writing, next one here bromine. Okay, like that, three molecules we are writing from second and third molecule. So total we are getting 6. Okay, these are also I am writing like here fluorine and bromine. Next, exchange of these two, iodine and chlorine, iodine and chlorine. Next, fluorine, iodine, double bond. Here we are exchanging these two, bromine and chlorine. Okay, by writing these molecules, sometimes we are going to select our answer as 6. That is a big problem. Okay, but what is the right answer for this question? 3 is the right answer. Why not 6? Now here once again come back to same question. What is the question here? How many of the following structural isomers of C2F, chlorine, bromine and iodine will show geometrical isomerism? We want structural isomers. What is the fundamental meaning of structural isomers? Molecular formula same, connectivity different. Okay, same molecular formula, right? But connectivities are different. Then those molecules comes under structural isomers. And what is the meaning of stereoisomers? Same molecular formula, same connectivity, but different arrangement of atoms and groups in space. Those molecules comes under stereoisomerism. But in case of structural isomerism, same molecular formula, right? But connectivities are different. Now just you look at this one. For some time, just you forget about spatial arrangement. Now come on to this carbon atom. Here, who is connected to this carbon atom? Bromine and iodine. Bromine and iodine. Here also same thing, on this carbon atom, bromine and iodine. Don't think about the spatial arrangement. Just on this carbon atom, connectivity is same or different? Bromine and iodine, bromine and iodine. Connectivities are same. Once connectivities are same, these two are not considered as different structural isomers. Both one are same. Structural isomers point of view, these two molecules are exactly same. That's why I am going to eliminate Now these structures are enough structural isomers which are responding for geometrical isomerism. Okay, these three molecules will show geometrical isomerism. Then what is the right option? 3 is the right option. Okay, that is our question. Right, come to the next question. Same type of question. This one also very important. Here our question is how many, somewhat lengthy but very important, how many structural how many structural isomers how many structural isomers of C3H3 fluorine chlorine bromine will show geometrical isomerism. Same type of question, just we are changing molecular formula, but here condition is given your compound is acyclic compound. How many structural isomers of C3H3 fluorine chlorine bromine will show geometrical isomerism? Same type of question, we are changing molecular formula. Okay, right. How many structural isomers will show geometrical isomerism? Now again we are approaching logical method. We have no formula here. First of all, you think about according to the given molecule. Here we have how many carbon atoms? 3 carbon atoms are there. With 3 carbon atoms, we have chance to write the cyclic. But here what is the condition given? Acyclic is given. Because of giving acyclic, now simply forget about thinking of that cyclic compound. Okay, so we want acyclic compound. And for geometrical isomerism, what is the condition? You should be with restricted rotation of bond. Okay, that may be CC bond, CN bond, NN bond, whatever it may be. Restricted rotation of bond should be present in the given molecule. Okay, so according to that given molecule, I am going to write like this: C double bond C, C double bond C. Why? Because if I want to produce geometrical isomers, minimum restricted rotation of CC bond I require. That's why out of 3 carbon atoms, you look at this one. What is the formula here? C3H3 fluorine chlorine bromine. According to the given molecule, first I am going to keep 2 carbon atoms in the part of double bond system, C double bond C, and I have extra 1 carbon atom that I am taking here. Okay, that is my first arrangement. Now about the structural isomers to produce the geometrical isomers. Okay, now just here I am trying to write structural isomers according to the given molecule. Okay, 3 carbon atoms are there. Out of 3 carbon atoms, 2 carbon atoms are joined by C double bond and another carbon atom is like this. Next one, here I am taking 3 hydrogen atoms here, 3 hydrogen atoms. After writing 3 carbons and 3 hydrogen atoms, now we have how many halogen atoms? 3 halogen atoms are there. These 3 halogen atoms we are taking like this. Now C, next one here also CH3. I am going to write complete structures of all molecules. Okay. Next I am trying to arrange halogen atoms. Now here I am taking fixed position of this methyl in these 3 structures. Now here I am taking fluorine and here chlorine. Next one here bromine. For example, if you are taking CH3 here, you have 3 possible options: fluorine, and what are the remaining halogen atoms? Remaining chlorine and bromine. Next one, after taking chlorine on this carbon atom, you have fluorine and bromine. Next one, bromine. Here fluorine and chlorine. These are the 3 possible structures. Now according to that first possibility, these are the possible structures. Now I am taking like this 1, and this is the second molecule, and here third molecule. These 3 molecules will show geometrical isomerism, right? Why? Because methyl and fluorine different, chlorine and bromine different, so that molecule shows geometrical isomerism. Like that, these 3 molecules shows geometrical isomerism. So first, how many of the structural isomers we are getting which are responsible for geometrical isomerism? Right now 3 molecules are completed. 1, 2, 3 molecules are completed, right? Next one, another molecules how we are going to write. Now come to second possibility. Again C double bond C. Here instead of taking simple CH3, I am taking 1 halogen atom here. CH2 fluorine. That is also one possibility. In place of hydrogen, we are taking fluorine. Next one, carbon, carbon. Here I am taking CH2Cl, CH2Cl. Next one, C double bond C. Here CH2 bromine, CH2 bromine. These are the three possibilities. In place of methyl, if one hydrogen atom is replaced by one halogen atom, you can replace one halogen, two halogens and three halogens also. Okay, we will try each and every one, but in the second stage what I am doing here, one hydrogen atom is replaced by one halogen atom. Then this is the situation. After writing this one, what are the remaining groups, remaining atoms? We have hydrogen. Next one, if you are taking fluorine here, and we have hydrogen, chlorine and bromine. Hydrogen, chlorine and bromine. So for example, if you are taking hydrogen here, then what about remaining arrangement? Here we can write chlorine and bromine. Chlorine and bromine. Okay. So not only this one, you can write three possibilities here. Same thing, CH2 fluorine, CH2 fluorine, C double bond C. Next one, CH2 fluorine, C double bond C. Not only hydrogen, you can take here chlorine also. Not only chlorine, even bromine also we can take. For example, if you are taking here hydrogen, remaining chlorine and bromine connected to other carbon atom. And what is the situation here? If you are taking chlorine here on this carbon atom, you can write hydrogen and bromine. Okay, right here bromine. What are the remaining possibilities? Hydrogen and chlorine. Hydrogen chlorine or hydrogen chlorine, not a word problem. Why? Because we are writing structural isomers. Totally we have how many possibilities? Three possibilities are there. Okay, three possibilities. Otherwise, let me do one thing here. Instead of writing 1 2 3, let me take 1 1 1, just in order to calculate total number of geometrical isomers. Now one molecule, again here also one molecule. Okay, right. And here this one shows geometrical isomerism, geometrical isomerism, again geometrical isomerism. Like that, try to arrange atoms from the second structure, right? C double bond C. Now here I am taking CH2Cl. Next one, C double bond C, again CH2Cl. If you are writing CH2Cl, then what are the remaining atoms? Hydrogen, fluorine and bromine. Here I am taking hydrogen, next one fluorine and bromine. For example, if you are taking fluorine atom on this carbon atom, remaining hydrogen and bromine. Okay, right. For example, if bromine is connected on this carbon atom, then what are the remaining atoms? Fluorine and hydrogen. Clear? These are the three possible structures. Once again, I am taking here 1 1 and 1. Okay, next come to the last molecule. Now here C double bond C, CH2 bromine. Next one, C double bond C, CH2 bromine, CH2 bromine. What about remaining atoms? After writing CH2Br, we have hydrogen, fluorine and chlorine. Here I am taking like this, hydrogen, next one fluorine and chlorine. Next, for example, if fluorine is connected to this carbon atom, remaining hydrogen and chlorine appears on this carbon. Next one, for example, if you are taking chlorine, then here hydrogen and fluorine. These are the three possibilities. Okay, I am taking like this 1 1 and 1. Once again, observe this molecule. If you are taking methyl here, how many possibilities are there? We have three possibilities. Next one, if you are taking CH2F, CH2Cl and CH2Br, 3 plus 3 plus 3, 9. 3 plus 3 plus 3, 9 possibilities are there. Okay, what is the another possibility? In another possibility, for example, if you are taking CH2 fluorine and chlorine, if you are taking two different halogen atoms. Next, what about remaining atoms? Remaining atoms we have hydrogen. Once again, after writing this one, we have hydrogen atom, next one bromine. Hydrogen, hydrogen, bromine, right? How to arrange this hydrogen, hydrogen and bromine? Now let us take hydrogen atom here and another hydrogen here. Next one, bromine. This is one of the structural isomer. Is it possible to produce geometrical isomers? Yes, we can produce geometrical isomers. What is the reason? CH fluorine chlorine is different from hydrogen and hydrogen is different from bromine. Yes, this molecule can show geometrical isomerism. For example, here if you are taking like this same type of molecule CH fluorine and chlorine. For example, bromine is connected to this carbon atom and remaining two hydrogen atoms connected to this carbon atom. This is also structural isomer, but from this structural isomer, now geometrical isomerism is possible or not? Geometrical isomerism not possible. If two hydrogen atoms, if you are connecting on the same carbon atom, geometrical isomerism not possible. That's why I am not going to consider this molecule. Okay, like that. Come to next molecule. What is next molecule? C double bond C. Okay, here I am taking CH. Here fluorine and chlorine completed. Next I am taking chlorine and bromine. I am leaving fluorine. Next one here CH, fluorine, chlorine, chlorine, bromine, and here I am taking fluorine and bromine. Okay, these are the possibilities. And what about remaining atoms? Similar to this one, here I am taking one hydrogen and one hydrogen, and what is the remaining halogen? Fluorine. I am not going to write other structures like this. And here fluorine, chlorine. Next I am taking hydrogen. Here hydrogen. What is the remaining atom? Chlorine. So here one molecule, one molecule. These are the maximum possibilities. Next one, for example, if you are trying like fluorine, chlorine and bromine, what are the remaining atoms? Hydrogen, 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 hydrogen. Is it possible to produce geometrical isomerism? No chance. That's why we are not going to take that molecule. Now finally, count the total number of geometrical isomers according to the given molecule. Come back to these structures. Now tell me this one. 1, 2, 3. 1, 2, 3. Next. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. These are the maximum structural isomers which can show geometrical isomerism. So for this question, what is the right option? 15 is the right option. 15 structural isomers will show geometrical isomerism. So 15 structural isomers, 15 structural isomers will show geometrical isomerism. Very important question. Okay, 15 structural isomers will show geometrical isomerism. So these two questions are very important. Once again, you look at the structures here according to the given question. How many structural isomers of C3H3 fluorine, chlorine, bromine acyclic will show geometrical isomerism? This is our right option. 15 structural isomers will show geometrical isomerism. 3 molecules, 9 molecules, next again 3 molecules. Okay, right. Next question. For example, this molecule is given like here hydrogen and hydrogen given. Here CH double bond CH, CH3 given. Left side also CH double bond CH, CH3 given. How many geometrical isomers are possible with this compound? Okay, it is visible, no problem. How many geometrical isomers possible with this compound? Here we are not applying any formula. Just to look at this one, among 3 double bonds, how many double bonds will show geometrical isomerism? This one as well as this one. But here geometrical isomerism not possible. With this double bond, we cannot produce geometrical isomers. Two double bonds will show geometrical isomerism. So what I am doing here, first I am taking hydrogen and hydrogen. Okay, instead of writing complete structures, Because of giving double bonded systems, just you write in the form of EZ nomenclature. Here I am taking and E, E and E combination. This double bond E configuration, this double bond also E configuration. And what is the next possibility? Hydrogen and hydrogen. Here you can write like this, one with Z configuration, one with Z configuration. This is the second possible geometrical isomer. Okay, next one, hydrogen and hydrogen. Here you can write E and Z. EZ or ZE, both one are same. Why? Because here identical atoms are given. Two hydrogen atoms are given. So totally we have how many geometrical isomers? 3. Very important question. Total number of geometrical isomers equals to 3. Okay, right. Don't get confusion. Sir, here only E and E present, H and H present. How geometrical isomerism is possible? Actually, here E configuration and E configuration, Z configuration, Z configuration, E and Z. These are the different arrangements according to the EZ nomenclature or EZ configuration. So totally we have 3 geometrical isomers. For example, this is the given question. Instead of giving hydrogen and hydrogen, if they are giving hydrogen and methyl. Next one, CH double bond CH CH3. Next one, CH double bond CH CH3. How many geometrical isomers possible according to the given compound? Total number of geometrical isomers. Okay, right. So what are the possible geometrical isomers? Here I am taking like this, hydrogen and methyl, hydrogen and methyl. I am not changing position of this hydrogen and methyl. Here we have how many double bonds? We have 3 double bonds. 3 double bonds can show geometrical isomerism. 3 double bonds. Why? Because here hydrogen and methyl, these two are what? Different. These 3 double bonds can show geometrical isomerism. Here hydrogen and methyl we are taking at fixed position and just we are trying to arrange configuration of remaining 2 double bonds. For example, left side you are taking E, right side also you can take E, no problem. P and E, this is one possible arrangement. Otherwise Z and Z, this is the second possible arrangement. Next one, here we can take E Z or Z and E. Why? Because E and hydrogen same side, sorry, E and hydrogen same side, Z and hydrogen same side. These two are considered as two different structures. Okay, that's why what is our answer? Total number of geometrical isomers equals to 4. Total number of geometrical isomers equals to 4. These are the special cases. Sometimes by applying formula we are not getting answer. Just by looking at the molecule, so we can get idea whether the answer will come from formula or from the structures. That means by applying or changing the position of atoms and groups. Okay, right. These are the 4 geometrical isomers possible for the given compound. Let us go to next molecule. Here, for example, NOH is given. NOH is given. By default, here how many lone pair? One lone pair is present. Again, same as previous, CH double bond CH CH3. Next one, CH double bond CH CH3. Here not only OH, even they can give simple hydrogen also. From both we are getting same number of geometrical isomers. Now same as previous. Yes, first I am taking like this, nitrogen hydrogen with lone pair of electron. Again, nitrogen hydrogen lone pair of electron, hydrogen lone pair, lone pair of electron. Okay, then what about configurations of both double bonds? Both double bonds configuration, so we can write like this, E configuration and E configuration, and here Z configuration, Z configuration. Next one, E configuration, Z configuration. Here Z configuration and E configuration. These are the possible arrangements. What are the total number of geometrical isomers? 4. Total number of geometrical isomers equals to 4. These are very important questions. Okay, right. Total number of geometrical isomers equals to 4. Come to next question. For example, molecule is given like this. CH tetrahedral carbon atom is given, remaining CH double bond CH CH3. Next CH double bond CH CH3. Next one CH double bond CH CH3 CH3. Okay, that is the given molecule. How many number of geometrical isomers are possible? So once a tetrahedral molecule is given, with respect to this hydrogen, remaining these groups are equivalent. Okay. So now here three double bonds are responding for geometrical isomerism. We can write like this: Z, Z and Z. Z, Z, Z. Hydrogen and this one and this one. These three groups are equivalent to hydrogen, right? That's why Z, 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 right? Next, what is another possibility? Z, Z, E. Z, Z, E, Z, E, Z, both one are same. Why? Because let me show that tetrahedral molecule. Okay, just you look at this one, tetrahedral molecule. One second. Yeah, this is the hydrogen atom. Z, Z, E or E, Z, Z or E, Z, Z. One and all same. Why? Because these three bonds are equivalent to that hydrogen. No change. That's why in case of tetrahedral molecule is given, this is our tetrahedral carbon atom. Okay, three double bonds are given. We can write like this: Z, 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 E. Next one, Z, E, E, Z, E, E. Don't get confusion from here. Z, Z, E, Z, E, Z, E, Z, Z. One and all same. These are same. That's why I am writing only one time. Okay, next one. What is another possibility? E, E and E. What are the total number of geometrical isomers? Total number of geometrical isomers equals to 4. Very important. Z, 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 E, Z, E, 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 E. Okay, right. Come to next question. For example, C, CH double bond CH, CH3. Okay, CH double bond CH, CH3, CH double bond CH, CH3. Next one CH double bond CH, CH3. That is the given molecule, right? What are the total number of geometrical isomers? Here how many double bonds which can show geometrical isomerism? 4 double bonds are there. We can write like this: Z, Z, Z and Z. Just to change one configuration among these 4: Z, Z, E. Z, 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 E, Z, Z, E, Z, Z, E, Z, Z, one and all same. Why? Because here tetrahedral carbon atom is given. Okay, right. What is another possibility? Z, Z, E and E. Next, Z, E, E and E. Last one, E, E, E and E configuration. What are the total number of geometrical isomers? 5. Total number of geometrical isomers equals to 5. That is the question. Okay, right. Yes, one more question. Yeah, this is the question. What are the possible geometrical isomers of the given compound? Possible geometrical isomers of the given compound. Okay. First one, just I am trying to fix this double bond. Okay. Double bond. Right. And what about the possible configurations? First I am trying with Z, Z, Z and Z. Okay. Right. Next one, Z, Z, Z and E. So wherever you are taking E configuration, that is giving again same structure of this one. Okay. For example, in the third one, if you are taking like this, Z, Z, E and E. Here we can take one more possibility, that is E and E on different carbon atoms. Here E and E present on same carbon atom, but here we are taking on different carbon atoms remaining Z and Z. Okay, right. What is another possibility? Next one, Z, E, E and E. Z, E, E, E. What is the next possibility? Somewhere one structure is missing. 1, 2, 3, 4. Z, 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 Z. Z, 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 E. Z, Z, E, E. Okay. Here we can write one more possible structure, that is E and E we can write in opposite direction also. You look at this one, E and E present on same carbon atom, E and E on different carbon atoms. Here E and E on different carbon atoms but in opposite direction. What is the next possibility? Next possibility, now here Z, E, E and E. E. Last one, E, 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 E. That is the answer. Okay. Here they are not asking structural isomers. What are the total number of geometrical isomers? What is the answer? Total number of geometrical isomers equals to 7. Okay. In first two questions, starting two questions, they asked what are the number of structural isomers which are responsible for geometrical isomerism or which can show geometrical isomerism. But in these questions, directly they are asking what are the total number of geometrical isomers from here. Total number of geometrical isomers 3. Total number of geometrical isomers 4. Total number of geometrical isomers 4. Here total number of geometrical isomers 4. Next one 5. And here total number of geometrical isomers equals to 7. Straight away they are asking total number of geometrical isomers. Okay, come to another question. For example, here sp3 carbon atoms are given, CH double bond CH CH3, CH double bond CH CH3, CH double bond CH CH3. And again here left side carbon atom CH double bond CH3, next to CH double bond CH CH3, CH double bond CH CH3. Total number of geometrical isomers of the given compound. Okay, right. What are the total number of geometrical isomers? First one, here what is the carbon atom? sp3 carbon and sp3 carbon atom, right? Here I am going to take like this. First one I am taking Z, Z, Z. Right side also Z, Z, Z. This is the first possibility. Okay, left side 3 double bonds with Z, right side 3 double bonds Z. Second possibility, Z, 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 Z and E configuration. Okay, somewhere I am taking E configuration. That E, whatever the position you are selecting, your result will be same. Now come to next one, Z, Z, Z. Next one here, E, E, Z. This is one possibility. I think this is the third possibility, right? Your question is directly total number of geometrical isomers. Total number of geometrical isomers. Now this is the third possibility. Okay. Come to next one. Fourth possibility. What is the fourth possibility? E and E we are taking right side. But we can take one more possibility, that one E left side, one E right side. That's why E Z Z. Next one E Z Z. Right hand side E at any position you can take. At any double bond you can take. That is not a problem. But one E left side and one E right side. And what is the fifth possibility? For example, if you are taking Z Z Z here, E E and E. 3E one side, 3Z other side. Sixth possibility, for example, if you are taking one E other side, like E, Z and Z. Next one E, E and Z. Something is missing. No problem. 3E and 3Z. Okay. 3E one side, 1E one side, 2E other side. What is the next possibility? Next possibility we are taking Z, Z, E. Next one E, E and E. That is the seventh possibility. And here we can take 2E one side, like Z, Z, E. Something is missing. 1 second. I am taking here 2E one side. Next one Z, 2E other side. 2E other side. Okay, right. What is the ninth possibility? Ninth possibility. I am taking one Z, remaining all are E configuration. E, E, E. Here only one possibility is there. Why? Because Z, either you are taking left side or right side, your result will be same. And what is the last possibility? E, E, left side all E configuration, right side all E configuration. This is our 10th possibility. Okay. So according to the given question, total number of geometrical isomers equals to 10. Total number of geometrical isomers equals to 10. Okay. These are the possible combinations. E, E, other side, 3E, 1E, one side, 2E, other side. Yes. Total number of geometrical isomers equals to 10. So these are the variety of molecules in geometrical isomerism. Okay. In today lecture, we are going to close geometrical isomerism, right? For example, if you want to practice type of questions from geometrical isomerism, now you can practice these molecules. Okay, no problem. These examples are sufficient, and I am not going to discuss about allenes, biphenyls and spiro compounds. Why? Because those are not important for mains and advanced, right? Almost no question is given even till today, right? These examples are sufficient. Okay, for example, if you want to do questions from allenes, biphenyls and spiro compound also, let me cover that topic also, no problem. Allenes, biphenyls and spiro compounds. So actually here we have even systems, even systems, even systems and odd systems, even systems and odd systems. Now in case of even system, we have even allenes, even allenes, even allenes, very simple, no problem, just 5 minutes. Even allenes, even spiro, even spiro, even biphenyls, even biphenyls, even biphenyls. Next one, odd allenes, odd allenes. Next one, odd spiro, odd spiro, odd biphenyls. Biphenyls. Okay. Geometrical isomerism point of view. Now, in case of even allenes, even spiro compounds, and even biphenyls, no geometrical isomerism, whatever the substitution given. But that condition also I will tell you. Now, in general, in even allenes, even spiro compounds, and even biphenyls, you don't find any geometrical isomerism. Next one, there is a chance for geometrical isomerism in odd allenes, odd spiro compounds, and odd biphenyls. GI is possible. This is the first important generalization statement. Now we have even systems and odd systems. In even systems, no geometrical isomerism, but in odd systems, we observe geometrical isomerism. Come to few examples. Now here I am going to take C double bond C double bond C. Now this is even allene because of the presence of two double bonds. Now this molecule is considered as even allene. Even allene. Next one, even spiro compound. Even spiro compound, but here condition is if substitution is given at extremely left and right carbon atoms, but not on other carbon atoms. Okay, left and right side, extremely left and right side, and biphenyls. These are even biphenyls. So whatever the substitution given on these carbon atoms, whatever the substitution, okay, irrespective of the substitution, here even allene molecule, even spiro compound, and even biphenyl, no geometrical isomerism is observed. No geometrical isomerism, right? But in case of odd systems, we observe geometrical isomerism. Few examples I am giving like this. Now C double bond C, C double bond, one second, C2H5. Next one here something like phenyl and COOH is given. Next one here phenyl and COOH is given, right? Here for example NH2 and methyl group is given. Next one here NH2 and methyl group is given. Okay, these are the given molecules. First one, you tell me this point. Now given system is even allene or odd allene. Now this is odd allene molecule. Three rings are there. This one odd spiro compound. Odd spiro compound. Why geometrical isomerism is possible in in odd allenes and odd spiro compounds? Now just you look at, this is our odd allene system. This is the even allene and this one odd allene. First you look at this molecule, even allene molecule, left carbon, middle carbon and right carbon atom. Clearly you look at this allene. Okay. For example, left carbon, middle carbon and right carbon atom. Okay. So conveniently just I am holding this molecule. What are the three conditions for geometrical isomerism? Restricted rotation and proper substitution. Next one, length we are calculating between two groups like L1 and L2. If L1 is not equals to L2, then that is geometrically different. If L1 equals to L2, geometrically same. That's why those molecules are not considered as geometrical isomers. For example, if you exchange these two groups, you will get same distance or different. Now you calculate length from here to here, L1. After exchange of these two groups, again you calculate distance L2. What is the relation between these two? L1 and L2 same or different? L1 and L2 are same. So once again you look at this one, whatever the distance between these two, L1, next one here L2. First one, before exchange, what is the distance between these two? L1. Okay. After exchange of these two groups, again you calculate the distance. This one L2. Same or different? L1 equals to L2. That's why geometrically they are not different. This is the real structure of allene. Okay. So because of that reason, even allenes not shows geometrical isomerism. Okay. Come to this R system. This is our R system. In R system, arrangement of groups are like this. For example, this is the L1 and L2 from here to here. Let me show from this side. Let L1, L2. Once again, same side. L1, opposite side L2. L1 is not equals to L2. Same thing we observe in spiro compounds. So because of that reason, R systems will show geometrical isomerism and even systems no geometrical isomerism. So whatever the substitution given on these carbon atoms, next one here on these carbon atoms, other than other carbon atoms, that means we are not giving substitution on these carbon atoms, just a substitution given on extreme left and extreme right. Whatever the substitution given at extreme left and right, no geometrical isomerism is observed in even systems, even allene and even spiro compound, no geometrical isomerism. And come to this R system. R system almost similar to normal alkenes. Here just you look at these groups. R system is given, right? COOH and methyl, same or different? They are different. COOH and methyl, same or different? Different. These molecules can show geometrical isomerism. In R spiro compound, CHO, C2H5, CHO and C2H5, yes, these molecules shows geometrical isomerism. Okay, right. Here I have given, okay, let me cover 1 2 examples for biphenyls. Last example, in case of biphenyls, now this one is given like CH3, something like tertiary butyl group. Next one methyl and tertiary butyl group is given. Okay, methyl and tertiary butyl groups are different, tertiary butyl and methyl groups are different, but no geometrical isomerism. What is the reason? No geometrical isomerism. Reason is distance same. Look at this biphenyl molecule. Yes, this is our biphenyl. So arrangement is like this. One is in vertical and one is in horizontal. So about the molecular models, clearly we will discuss in optical isomerism in the representation of molecules. Now just to look at these rings, right side ring and left side ring. Right side ring arrangement vertical, left side ring horizontal arrangement. Just to calculate the distance between these two. Now let me show this one. What is the distance between these two? L1. For example, if you calculate the distance between these two, L2, same or different? Same. That's why in case of even systems, no geometrical isomerism is observed. For example, R systems given, tertiary butyl and ethyl, right hand side, tertiary butyl and ethyl. For example, here groups arrangement is like this. This is the R system. So whenever R biphenyls given, remember this point, you completely forget about that middle ring system. We don't want anything about middle ring system. Just you look at left side and right side. Here tertiary butyl group and ethyl, same or different? They are different. Tertiary butyl group and ethyl group, same or different? Different. So this molecule can show geometrical isomerism. Okay. This is the story about allenes, biphenyls and spiro compounds. Now you remember this point. We have even systems and R systems, even allenes, even spiro compounds and even biphenyls. No geometrical isomerism is observed. Odd allenes, odd spiro compounds and odd biphenyls we observe geometrical isomerism. For example, question given like this. Calculate total number of geometrical isomers. Phenyl, CH double bond CH. Next one, CH double bond C double bond C H. Okay, and here they are giving odd spiro compound, odd spiro compound. Okay, next one something like C double bond N OH. What are the total number of geometrical isomers of this compound? Okay, how to calculate? Now this double bond can show geometrical isomerism. Next one here, what type of system given? Even allyne system or odd allyne system? It is odd allyne. This one also considered as one segment for geometrical isomerism. For example, even given, that will not show geometrical isomerism, but odd system will show geometrical isomerism. Next one, odd spiro compound or even spiro compound. Now this one even, sorry, odd spiro compound, and as usual this oxime will show geometrical isomerism. Totally we have how many segments? 4 segments are there. Unsymmetrical molecule, 2 power 4 equals to 16. 2 power 4 equals to 16. Okay, now these are the total number of geometrical isomers according to the given molecule. So one more example I am giving. If compound is given like this, phenyl ring system, next one here also phenyl ring system, somewhere they are giving CH double bond N OH, CH double bond N OH. Okay, next one here something like tertiary butyl group, ethyl and something like group is given like this. Okay, now phenyl ring systems are what given? Even phenyl ring system, sorry, even biphenyl or odd biphenyl according to the given molecule. Your molecule is even biphenyl. About even biphenyl, we cannot produce geometrical isomerism. So simply forget about this one. And we have this particular segment. Here we can produce geometrical isomers. What are the total number of geometrical isomers? 2 power 1 equals to 2. Your molecule is unsymmetrical molecule. Directly I am applying 2 power n. And how many segments are there? One segment is there. Okay, about which we can produce geometrical isomerism. Right. Now this is the story about geometrical isomerism. For example, if you want to do practice on this geometrical isomerism, you can take screenshot. Here the question is, how many of the following molecules can show geometrical isomerism? I am giving numbering. If possible, we will discuss in the next class. Third example, 4, 5, 6, 7, 8. Number of molecules which can show geometrical isomerism. Yeah. Next page. 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 20 molecules. How many of the following molecules will show geometrical isomerism? That is our question. 20. Next, 21, 22, 23, 24, 25, 26. Next, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42. 49, 50, 51, 52. Sometimes very tough questions are also they are giving. That's why I am giving these examples: 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 64, 65, 66, 66. Totally 66 questions are there. Once you try to practice these questions, really if you want answers for these questions, please write on the comment box. Definitely I will discuss and I will make one video about these questions. Okay, thank you.